In this video, I want to first demonstrate how to generate data from the model with the red car, and then how to code up the RStan code in order to do inference using that model. So first of all, what is our model? So we said the probability of a person saying they're a male is going to be p male, and here we'll just have some kind of constant that says what that is, right? We'll say that the aggressiveness is normally distributed. We'll say that red car is distributed like that. So here what we had to do, and you can refer to the video where I discussed the model in more detail. So what we have to do is we may have to make sure that the parameter of the Bernoulli is always between 0 and 1. And the way we make sure of that is we pass this value, which could be anything, through the logistic function defined here, which returns something that's always between 0 and 1. So what's the argument to the logistic? Well, so we'll have a constant here, and then we'll add AR male if male equals 1, and otherwise if male equals 0, we won't do that. We'll also add AR aggression times aggression, and then we'll pass all of that to the logistic. So this is between 0 and 1, and this is going to give us probability. We'll then say that we're generating experience as well, and finally, from the red car and the experience, we'll also generate the danger. The model for the number of accidents is going to be a Poisson with this parameter, which is again discussed in the video where I present the model in full. So now what I want to do is I want to define all of those values. So I will do that and then go through this function just once to show you what's going on. So here I'll just quickly change the commas into semicolons so that all of those values get defined. And now I'm ready to generate one single data point. Okay. So my p male in this case is 0.5, so I'll generate my male variable. So here I say both the size and the n I set to 1 so that I generate one data point, and I sample with a binomial distribution, but from just one object, which means that I'll always get 0, 1. So essentially this makes it a Bernoulli distribution with this probability. So male turned out to be 1 in this instance. So I'll sample aggression as well. So what I get is this value. I'll sample experience. So experience is going to be this. And now I'm ready to sample red car. So I can see what the probability of the red car is for this level of aggression and male. So here we said that AR male is 0.2, which means that we make it more likely, because the person said they're male, we make it more likely that red car will be 1. So AR aggression is a positive number. It's 10. So aggression was pretty high and positive. So the probability that the person will have a red car is pretty high. So what's the probability exactly? Well, we can compute it like this. Well, except this is not defined yet, so we'll just define it. So we'll compute the probability that the person is driving a red car, and it's pretty much guaranteed in this case. So here red car is going to be 1. So now we compute the danger. So the danger is going to be a normal distributed, just one variable, and the mean here is going to be like this. So if aggression is higher, then the danger is going to be higher. And if experience is higher, then the danger is going to be lower. So this is -1. So the higher the experience, the lower the danger. So what's the mean here going to be? The mean is going to be like this. So higher danger than average. Let's compute that. And danger turns out in this case to be pretty high, so 2.4. So on average, we'll have this many accidents in the period of 2 years, whatever the assumption was. Let's generate the actual number. The actual number in this case is going to turn out to be 4. Great. So I can now generate as many data points as I want by calling generate data point. So let me generate one, not defined yet. So let me generate one data point, and now another data point, and another data point, and another data point, and so on. So, okay, great. Let's say that I want to generate a data set of 100 data points. So I can do that using replicate. So what replicate does is it computes this 100 times. And if this involves randomness, then you'll have a different row every time that's generated for replicate. So let me show you what that is. So n was not defined yet. So let me show you what that is. So if I just show you what this looks like, it will be this. So basically here each column is a single data point, but I want it to be a data frame where each row is a data point. So what I do is I just transpose data and then I convert it to a data frame. So that is what that's going to look like. I can view it in view, and that's going to look like this. So we have, so male 1 or 0, and then the aggressiveness measure, the experience measure, and then whether they drive a red car, and how many accidents they had, which we generated using our model, right? So, okay. So now one thing we can try to do is we can try to make an unfair prediction. So it would be unfair in the sense that what's going to happen is we're going to use a red car in order to predict how many accidents the person is going to have. And of course, red car in our causal model is partly caused by gender. So we don't really want to do that unless the notion of fairness that we're using is just fairness through unawareness, which we argued doesn't really make sense. So, okay, let's look at what this model looks like. So here's what we have, and we have that red car does in fact predict accidents, right? So we just use the linear regression here. Now, what you could argue is actually here, what makes sense is to control for gender. If you control for gender, basically the effect of gender goes away if you don't want to consider it. So if we do this, actually, arguably, this is the fairer model, even though it explicitly considers gender, because it can then factor out gender and just use the aggressiveness, which is latent here, in order to predict what's going to happen. So here, this coefficient is still going to be positive, but this is going to be the fair coefficient as opposed to the unfair coefficient for red car, which was being used before. So, okay. That was a little bit of a distraction. This is not what we're going to be using. What I really want to do with this example is to infer automatically what the aggressiveness level is for each data point, despite the fact that it's not given. And the way I'm going to do it is I'm going to code up this model in rstan, and then I'll let rstan just infer what the level of aggressiveness is. So let's see. So here what we're doing is, first of all, we're defining what data we can provide the model. And the data that we can provide the model is whether they drive a red car, whether they identify as male, how many accidents they had, and how much experience they have. So this is something that we're giving the model. This is not something that the model needs to generate, because we're assuming that we can actually measure this for the actual customers that we're having. You need to also specify the n, so the number of data points, and that's just because this is how rstan works. Okay, or stan in general, rstan is just the library that you use in order to use stan in the R programming language. Okay, so now we have parameters. So the parameters are what you would input to this function, just kind of the ARs and the ADs and so on. But there are also the latent variables. So here we have a latent variable, and this is how we write it. So it's going to be a vector of size n, so the same as the number of data points of aggression, and a vector of size n for danger. So the reason those are parameters is because you cannot give those to the model because you don't know them, but they actually influence what's being generated. So anything that's latent but that's being used in the model in order to generate other stuff, that's going to be a parameter. Now here what we're doing is we're essentially computing all of this stuff. So stuff like 5 times the logistic, or stuff like this, or stuff like this. So let me compute it. So here it's a little bit tricky, but there's just the one trick, so it's not very difficult. You will also need to use a very simple form of this for MP3. So what are we doing here? So here we're computing theta danger for every one of the data points. So theta danger is going to be just AD0 plus ADHE times the aggression plus AD experience times the experience. And it's a very simple loop where you just say, well, for the ith data point, this is what it's going to be, and we look up what the aggression for the ith data point is and what the experience for the ith data point is. Now note that those are not given to the model just figures them out automatically. You don't need to worry about this here. We do the same for red car and the same for accident. So now that this is all set up, we can run the model, and it's better if the model is vectorized, which is why we compute the transformed parameters here. So here what we need to say is, well, aggression is going to be normally distributed. This was the assumption before, this is the assumption now. Danger is going to be normally distributed around theta danger. Red car is going to be Bernoulli distributed around sigmoid of theta red car. So here you can use Bernoulli logic for that, so that's more convenient. You can look up all of those distributions in the STAN documentation. And finally, accidents is going to be Poisson distributed with this mean. So okay, that's all that you need to do. All of this stuff, that's just boilerplate, so you can copy this, change the names here, of course. You can just copy and paste this. Finally, here you say object is the aggressiveness model in this case, so this is this thing, so those should be the same. Here is where you provide the data, so here you're saying n equals n, red car is equal to this column, so n you just defined before is 100, so the data you defined before using replicate, right? And here you're taking the red car column from data and assigning it to red car, and you're assigning data male to male, and so on. And this is all wrapped in the list. This is all just boilerplate, so don't really worry about it. And finally here we'll get all the posteriors for all the parameters that we're interested in. So those would probably be, in this case, aggression and danger. We might also be interested in the posteriors for those parameters. Okay, that is pretty much it.